Good morning, friends, or good afternoon, depending upon when you're watching this. Today we are going to graph our atmosphere's layers, as well as take a couple of short notes about those various layers. So how do we actually study the atmosphere? How many of you are thinking satellite? Well, you're correct, but a satellite only gives us the picture from outside most of the Earth's atmosphere looking down. It's great to see cloud formations and weather patterns, but it doesn't give us the whole story. Oh, now you think airplanes. Again, you're not incorrect, but you're not fully correct either. What if I told you that airplanes only fly most of the time in the lowest part of our atmosphere? The right answer is actually something much less sophisticated. It is weather balloons. So here's a short video that shows you how we send up weather balloons.
The Upper Air Program here at the National Weather Service is a critical part of our everyday operations. It is the only way we have to actually sample the atmosphere all the way up to about 100,000 feet. Well, here at the Upper Air Building is where we actually go through the process of filling up the weather balloon. We use helium here at this office. Other offices also use hydrogen. And here on a standard day, we'll put about 1,200 grams of helium in. We launch rain or shine, hurricanes, blizzards, pouring down rain, anything except for lightning. If we hear any thunder within 15 minutes, we cannot launch the balloon. To repair the radiosonde, we take it out of the box, take a look at it, make sure all the sensors are working properly. We have a hygroscope that measures humidity, temperature boom that measures temperature. Since all of this is GPS based, which you'll see up in the dome right there, we have to make sure that the radiosonde at the office is picking up the correct number of satellites. So we let it sit there for a few minutes to make sure it's catching all the satellites, make sure all the temperature data is correct. Once that is ready to go, we can bring the radiosonde down here and launch the balloon. We attach a parachute, so when the radiosonde does fall to the ground, it won't hit anybody, hit anything, cause any damage. After that, we will attach the parachute and the balloon to the radiosonde. After that, we launch the balloon. It gets to about 100,000 feet, takes 90 minutes to pop, and then we quality control and monitor the data for the next 90 minutes. These observations, after we take them, are carefully quality controlled by our staff, and then all of the observations go into our models to help us forecast. We also use the raw sounding data to actually help us with severe weather, rain snow lines when it comes to winter weather, and also helping us out with various other temperature and dew point predictions.
All right, so weather balloons, as you can tell, collect a lot of data, and they are launched twice a day, every day, all over the world. And data that radiosonde collects includes temperature, pressure, humidity, as well as wind speed and direction. So here is a surface map of basically some of it's not even raw data, it's actually been calculated data at this point. But what I want you to notice is that each one of these blue dots represents a National Weather Service location. And it is at these locations that they are sending up the weather balloons twice a day, every day, 365 days a year. And as we start our study of weather maps, you'll actually be able to read this and make more sense of what it means. So what I would like for you to do now is to take out your graphing the temperature of the atmosphere, and you will see that you have a quick introduction as well as directions. Please familiarize yourself with those. Then I want you to be very careful. I want you to notice that along the x-axis of your graph, you have your temperature. Put your finger on 0 degrees Celsius. You will notice that it is fairly far to the right, and that most of what you will be working with today are negative numbers. Remember that negative 18, for example, is larger than negative 49. Okay, so negative 18 is closer to 0 than negative 49. Notice also that you have two columns here that you need to graph. So you have altitude from 0 to 48, And then in the second column, you have altitude from 52 to 100. So I would like for you to pause me. You are going to graph this data. If it looks wrong, it's right. All right, welcome back. At this point, you should have created a temperature graph that looks something similar to this. And that's why the last thing I told you is if it looks wrong, it's right. Because generally, we think about the temperature of the atmosphere as decreasing with altitude. And we actually see that while that is true for the lower part of the atmosphere, something weird kind of happens up in here, and it actually gets warmer before getting colder again. So let's take a look at these different levels, because this is how scientists determine the different layers of our atmosphere. So the first thing I would like for you to do is draw a line straight across at about the 12-kilometer mark. Remember that at any point you may pause me or rewind to make sure that you're able to get your notes. I would also like for you to add at 8 kilometers, that is about the summit height of Mount Everest. So even if you summit the top of Mount Everest, and generally flying in a commercial airplane, you will spend your entire life in this lowest layer called the troposphere. Tropo means changing, and it specifically refers to the fact that this is where our weather occurs. The troposphere is the densest layer of the atmosphere. And that's pretty easy for you to think about. Remember that we live at the bottom of an ocean of air. And the densest layer is always going to be at the bottom. So the analogy here, of course, is Earth's layers. Our densest layer is going to be the core, while the least dense layer is going to be the crust. Well, the opposite is true for the atmosphere. Okay, we're going to live in the densest layer because it's at the bottom of the atmosphere. So what force actually holds the atmosphere to Earth's surface and doesn't let it fly away? Well, my friend, it's the same force that holds you here and doesn't let you fly away. It's gravity. So then think about this. Where is gravity going to be the strongest in our atmosphere? You got it, right here at Earth's surface. And they've actually done some very careful scientific experiments with very carefully calibrated scales. Because remember, when you measure your weight, you're actually measuring the pull of gravity on you, and that we are heavier at the bottom of a skyscraper than we are at the top of it, ever so slightly. So I've always liked this picture here on the left. So notice that most of our molecules of air are going to be right about sea level. Well, friends, we live in Florida. We live at sea level. And this is why, especially if you go skiing out in Colorado, you may feel like you are more out of breath or that you are panting for air with the same type of activities that you can do at sea level and not be out of breath. And it's because there is actually fewer air molecules when we are at altitude or at elevation compared to when we are at sea level. I've also found it fascinating that this is why we train a lot of our summer athletes in Colorado Springs, Colorado. So our swimmers and our track and field runners, the Olympic training site for them is in Colorado Springs. And the reason is we get them used to training their muscles at an oxygen deprivation level in Colorado Springs, and their muscles get bigger and used to carrying more oxygen. And then we bring them very often back down to around sea level for the Olympic Games so that their muscles are big and strong and ready to help give them some of their best athletic performances. The next thing that I would like for you to do is to draw a straight line across at the 48-kilometer mark. You may need to add this one in between 45 and 50. You are going to label this as your stratosphere. Strato means spreading. And the big thing with our stratosphere is that it contains our ozone layer. And our ozone layer's job is to block most of the incoming UV rays from the sun. Doesn't block all of them because we can still get a suntan or a sunburn if you're Mrs. Gerhardt. But it does block enough of them that life as we know it is able to thrive on Earth's surface. If we didn't have this ozone layer, it's very likely that these ultraviolet rays would not allow life as we know it and would kill much of the life that we do have. And then I'd also like for you to include at 36 kilometers the strato jump. Okay, so you guys are probably a little too young to remember it, although you may have heard about it. That we had Felix Baumgartner and Red Bull, yes, Red Bull gives you wings, who were actually kind of pushing the limit of the human body and human endurance. And they took him up to 36 kilometers, and his only way back down was to jump. So I'm going to show you about a 4.5-minute video of Felix's jump and the kind of that whole day leading up to his successful attempt. I hope you enjoy.
We got to get Felix off the ground safely and not tear the balloon. And we need optimum conditions. So as the weather person here, we're going to be very, very, very picky and picking the right conditions.
Felix has completed his physical.
I've been working 4 years on the program. I believe in what Felix is trying to do, to test the next generation full pressure suit. And I'm just delighted to be a member of the team.
This is Mission Control at this time. Felix is departing his Airstream trailer to be strapped into the Stratos capsule.
I will assess the situation again. We will not start inflating as soon as the balloon's completed laying out. So there'll be another small hold.
T-minus 1 hour, 13 minutes. We're going to go on hold.
Chuck Yeager was the first man to go supersonic in an aircraft. It was 65 years ago, and I think it would be just absolutely wonderful if we could get Felix to go supersonic without an airplane on the same day that Chuck Yeager flew supersonic in an airplane.
At this time, we have begun balloon inflation. Capsule systems are green, instrumentation's green, payload's green, medical systems are green.
There's the release, and there's the applause. A successful ride.
This is Mission Control. Felix's current altitude is 25,300 feet.
We're at 108,000 feet. There is an issue with the heat in the faceplate. Mission for the time being is continuing as the team considers what are the options. So the decision has been made. Baumgartner will jump.
The whole road is looking down. Sometimes you have to get up really high. How small you are. I'm going home now.
Jumper away. Speed 650 miles per hour. Speed 725. Speed 720.
when you're standing out there on that step, top of the world, you become so humble. At that moment, it's not about breaking records anymore.
Pretty incredible, right? I've always loved this meme. Hope you get a chuckle out of it too. So the next thing that I would like for you to add to your graph is a straight line across at 84 kilometers. You are going to label this as the mesosphere. Meso means middle. And the major thing about the mesosphere is that it protects us from meteors. This is where they burn up. This is the first place in our atmosphere that they encounter enough air particles that there is friction, that they begin to give off that shooting star look, if you will. Now, I want you to first label your thermosphere. Okay? Thermo means hot. Think about a thermostat or a thermos. This area is very, very thin, and it's very hot because the particles are moving quickly. It doesn't mean that it is very warm in terms of temperature because these particles are so spread out, they don't touch one another very often. And gradually, this area is going to bleed out into what we call space. And our designation for space is the 1,000-kilometer mark. So in reality, you would actually have to stack 9 of these graphs on top of each other to get to space. Because the thermosphere is so large, it actually behaves differently depending upon where you are. The lower part of the thermosphere is called the ionosphere. It has electrically charged particles called ions in it. And this is how we bounce our radio signals, as well as our auroras. So both our northern and southern lights happen in the ionosphere. The exosphere, exo means outer. Think about like an exoskeleton. And this is where satellites in the International Space Station will orbit. I'm going to show you 2 videos.
With spring right around the corner, it's the season for auroras. Also known as the northern lights, auroras are the brilliant curtains of colored light that appear in the night sky in the far northern or southern regions of the world. Although auroras are spectacular to watch, they're actually a manifestation of violent space weather. These are just caused by energy coming into our Earth's magnetic atmosphere, causing the whole magnetic field to reconfigure and end up with an explosive release of high-energy electrons and protons into our Earth's atmosphere, where they strike the molecules, both oxygen and nitrogen, and cause them to glow. Besides igniting the northern lights, these substorms can create big problems here on Earth by disrupting power grids, satellites, air travel, and even GPS signals.
All right, and then the second video I want to show you is actually the auroras from the International Space Station. This one's really cool because you can actually see the ionosphere. So if I paused here, you are able to see that this line of the green is going to be the bottom part of the ionosphere, and that this top part is going to be the upper part of our ionosphere. So you're able to see the kind of layers of our atmosphere. So we see the troposphere here in orange. And then the pink, kind of white, is our stratosphere. And then the light blue is our mesosphere. And then it gradually fades out into the thermosphere and into space. And then here is one, I believe that this is Space Shuttle Endeavour. And you have the same thing. So this orange is going to be our troposphere. The white is our stratosphere. The blue is the mesosphere, and then you can see that we get this slow fade out to black, which is space. So this protective envelope is what keeps us safe and warm and able to breathe here on Earth. It is one of the most important natural resources that we have.